So, we're going to be doing some applications of vectors. Things like boats moving in a certain direction and then turning and moving another direction. Planes flying in one direction and then moving in another direction. What we need to do is marry the way that people in the real world talk about those things and the way that mathematicians talk about those things. And we need to be able to seamlessly move from here to math world and from math world back into the real world, do our calculations and come back again. If that's confusing, don't worry. Okay, so how do people in the real world talk about like directions that they're flying in? Hopefully you've heard of something called a true bearing before. Let's just do one arrow. That's the north arrow, right? Now, if you want to tell someone what direction to face in, it's very, very straightforward. You say something like, I would like you to go 70 degrees true. And the way that you do that is by starting at north and rotating clockwise, right? Start here, rotate clockwise, and measure an angle of 70 degrees. Okay, this is in the real world. You start by facing north and you rotate, very important, clockwise. But in math world, we don't really think in terms like that. Instead, this is our default direction, right? The positive direction of the x-axis, I guess you could call it east. So if we wanted someone to travel in that direction, or if we wanted to represent this direction in our mathematics, we wouldn't use 70 degrees. We would use a different angle. Now, you can figure out what that angle is. If we start at the x-axis and we rotate anti-clockwise, maths people go anti-clockwise, right? Start here, rotate here. Now, if that's 70 degrees, this bit here must be 90 minus 70, which is 20 degrees. All right, so in the real world, 70 degrees true. In the math world, we would say that that's equivalent to 20 degrees. Oh, why the ambiguity? What's going on? Well, that's just how the world works, right? Like, we learn, maths is a language, and so languages have different ways of speaking about different things. Okay, so why is it useful to be able to do something like this? Well, remember, when working with vectors, we often convert from component form to polar form or from polar form to component form. And when we were converting from polar form to component form, we had a formula that looked like this. Right, and we could convert from this angle, we could use that angle in this equation, and we'd be able to figure out what it is in component form. So that's why we sort of need to be able to work like this and not just stay here. All right, let's just convert a couple of others. Now, the important thing to note is there is no like hard and fast rule for how to do this conversion, right? Not that I'm aware of anyway. What you need to do is draw the picture, look at the angles, think about it, and then convert it into this form. So let's take a look at a different direction. So in the real world, someone said something like 230 degrees true. I start by drawing in a little compass rose. That's useful for me. Start by facing north. I rotate clockwise. Now, how far? Well, 90, 180, right? And then 230 minus 180, I need to go an extra 50 degrees. And let's say that bit there is 50 degrees. The whole thing altogether is 230 degrees. Okay, and then we need to take that and convert it to math speak. So again, I draw in my thing with an arrow there this time. I'm going to draw that in, and I'm going to label an angle that I know about. I know 50 degrees. Not a very good drawing. Now that's 50 degrees is not the answer, but I just think it's useful. Okay, how would a mathematician do this? They would start by facing this direction and rotating anti-clockwise 90, 180, plus whatever that is. If that's 50, this bit's 40. Which means that the whole thing is 90, 180. 180 plus 40 is 220. So, 230 degrees true is equal to, in math talk, 220 degrees. Hopefully that's not too confusing. 330 degrees true, what is that? Okay, well, 330 degrees true, we start at north, we rotate 330 degrees. Now, if I rotated 360, I'd be there. But I'm not rotating 360, I'm rotating 330. So come back here by 30 degrees. Boop. So that angle there is 30 degrees. That's useful. But this is the 330 degree true. Okay, 330 degrees true. In math speak, we start by facing in this direction. Let's draw in the thing there. I think that angle is going to be very useful to know about. We start here and we rotate anti-clockwise. 120 degrees. 120 degrees. Now, of course, you could go the other way, right? If a mathematician spoke to you, you could convert it to like what a plane would do or a boat captain would think about. So a mathematician says 350 degrees. And you understand that to be start here and rotate anti-clockwise 350 degrees. If you did 360, you'd be back where you started. So back a little bit by 10 degrees. That's 10 degrees there. Okay, so all the way around from there to there is 350 degrees. That's what a mathematician thinks. In the boat captain world, draw in your line. That angle that I just wrote about is really important, that 10 degrees. And a boat captain would just say, no, I want to go, start from here, rotate clockwise, 100 degrees true. Okay, so you can see, drawing these pictures, because I honestly, I don't know if there's a formula for this. I don't know if there's a formula to get from there to there, from there to there. If you can invent one for me, you go ahead. I would love to hear about it. If you've invented a formula to convert true bearings to math bearings. But I think the best way to go about it is to draw a picture, look at the angles that you think are interesting, and then think yourself, how do I come up with what the true bearing is, or how do I come up with what the math bearing is?